Hello again, AP Stats. This is Mrs. Harding. Today we're going to be going over Activity 2.2a on density curves and normal distributions. At the top of your screen, you should see the learning objectives for today, using a density curve to model distributions of quantitative data, and then using the 6895-99.7 rule, which is also called the empirical rule, to estimate the proportion of values in a given interval of a distribution, and to find a value that corresponds to a given percentile in a normal distribution. So remember percentile from the previous lesson. So let's get started with density curves. At the top of the activity, it just kind of is refreshing your memory about what we've done so far with distributions of data. We've created displays, graphs. We've looked for overall patterns. We've discussed shape, outlier, center, and variability. We've also come up with a few specific numerical summaries of the data for center and variability, mean, median, IQR, standard deviation, range. We've used all these things to describe a distribution. A density curve is another way to describe a distribution. If you just quickly flip to page 2, you have a distribution there of vocabulary scores. The distribution, if you were to describe the shape, would be symmetric, unimodal. And over the top of it is a smooth curve drawn, and this is called the density curve for the distribution. This generally follows the shape of the distribution. These density curves are mathematical models for the distribution. As you can see, they're not exactly a perfect fit. They're just an ideal description of the shape of the histogram. So let's actually go back now to the first page. There was a distribution there that I had you skip over temporarily. Oops, don't mind my scrolling. We got to get ourselves back up there to the first page. There we go. And if we were going to draw a density curve over the top of this one, it might look something like this. We might go here and here. And you'll notice that my curve that I've drawn isn't a perfect fit. It certainly doesn't go all the way up to the top of that top bar, but this is just a model that we can use to work with the distribution and to make predictions about the distribution. All right, let's go back to the second page. One of the things that's very important about density curves is thinking about the area under the curve. So when you look at the amount of the histogram that falls onto the curve, or the percentage of the data, 100% of the data is represented by all the bars in the histograms. If we write this as a proportion, that's 1. So what we're going to look at is the area under the density curve being 100% of the data, or the area being 1. So then we're going to be able to talk about what percentage of the data falls in a certain area of the density curve based on the area that is shaded in. If you go to the next page, we're looking at a distribution of information about a math placement exam. And at the top, it says we're going to shade in the histogram showing the scores that range from 0 to 7. You can see that here on the graph. These bars right here represent the scores from 0 to 7. And then the question asks, what is the total proportion of data that falls in that range? And you can certainly determine that by figuring out there are 55 scores within that range, 209 total. So it's about 26% of the data. If we went back to that very first picture on the first page of the same data, this was the density curve that we had created, and if we just shade in which portion of that is from 0 to 7, we're looking here at this portion of the density curve. And if you had to make an estimate here of what portion of the data this is, you would estimate probably around 25%. So you can see that 25% of the area of the density curve corresponds to 26% of the data that falls within that range. Now we're going to start focusing in on density curves that are unimodal and symmetric, and we'll talk about those being called normal curves. But let's just, before we get to that, just talk about the book definition here for a density curve. You can see the criteria there. Density curve is a curve that is always on or above the horizontal axis, has area exactly 1 underneath it. And the density curve describes the overall pattern of the distribution. So while we're going to focus in on unimodal, symmetric, approximately normal distributions, density curves can be used to describe any shape. So at this point, I'd like you to pause the video and answer those questions underneath Check Your Understanding. All right, so is this a legitimate density curve? It is above the x-axis and the total area is 1. What proportion lies between 7 and 8? You can see the area there says 0.12, so that's 12% of the data fall between 7 and 8. And you can see in there where the median and the mean are marked. These are not exact locations, but you should have the mean to the left of the median because this is a distribution that is skewed to the left. Okay, on the next page, we're going to begin talking about the normal curve, and we're going to start to focus in on this shape. The normal curve is a theoretical model for data distributions that are unimodal and have a symmetric bell shape to them. We typically refer to these as approximately normal. You know that real-world data, actual data sets are not going to be exactly normal, so we refer to distributions that look like this as approximately normal. Now, when you're talking about a normal curve, because the shape of all of them is the same, unimodal, symmetric, there are only really 2 things that we need to know to draw the graph and to describe it. Those 2 things would be the mean, represented by the Greek letter mu, and the standard deviation, represented by the Greek letter sigma. So because all of the normal distributions have exactly the same curve, we only need those 2 pieces of information to make a sketch. And you can see what I'm highlighting here on the screen. This is often how a normal curve is described, with the first value, mu, being the mean, and the second value, the standard deviation. Now, if you take a look at the 2 curves that are there on the screen, you can see they have very different standard deviations. The standard deviation, in general, the distance from the mean to 1 standard deviation out, is the point on the curve where it changes from concave down to concave up, sometimes called the inflection point. This is equivalent to 1 standard deviation. And depending on the variability here, remember standard deviation is a measure of variability. It could be small, it could be large. But it is this point here where it changes from concave down to concave up. Something that you can't necessarily see from the picture but is important is here. The curves extend infinitely along the horizontal axis and are asymptotic to the axis. Well, that's a fun little word, right? Remember what an asymptote is. It approaches but does not reach or cross over. So even though you can't necessarily tell in this picture, just because of the way that graphics need to be drawn, the ends of the normal curve do not touch the x-axis. They continue on infinitely. Let's return to our math placement exam data. First question you see there, will a normal density curve model this situation fairly well? Remember, we're talking about modeling and it's not going to be a perfect fit. We're looking for, is it unimodal and symmetric or bell-shaped? And in this case, yes, it is. So what we can do is we can find the mean and standard deviation of this data, and we can use it to make a model. Are they exactly the mean and standard deviation for the density curve? No, but they're close, and we'll talk about that more later. So you can see the mean score is 10.22. The standard deviation is 3.88. So what I would like you to do at this time is I would like you to try to answer parts C through E on the next page. You can check your answers here. In part C, we're looking at the mean plus and minus 1 standard deviation. So within that range was about 68% of the scores. Take a look at part D. What percentage of the data falls within 2 standard deviations? So now we're looking at between 17.98 and 2.46. That ended up being 95% of the data. within 3 standard deviations ended up being 100% of that data. So these percentages that you just found are relatively the same for all normal distributions. Remember that the ends of a normal distribution continue on forever, so we're not going to say 100% of the data falls between any two values. Sorry, my screen's freezing up here a little bit. There we go again. But this is generally how the data within a normal distribution will fall. You can see mu is in the middle. Here, this is 1 standard deviation out. This is 2 standard deviations out. This is 3 standard deviations out. So typically in a normal distribution, 68% of the data is within 1 standard deviation. 95% of the data is within 2. 99.7% of the data is within 3%. I apologize, within 3 standard deviations of the mean. The remaining 0.3% is divided evenly on the ends, and we can't say for sure that it's within 4 or within 5 or within 6. It's just more than 3 standard deviations out. So that final 0.3% is just said to be more than 3 standard deviations from the mean. And here on page 8, it summarizes that underneath the empirical rule. 68% within 1 standard deviation of the mean, 95% within 2, and 99.7% of the observations fall within 3 standard deviations of the mean. So in problem number 3, I'm going to actually do this one with you. It says, as a group, the Dutch are among the tallest people in the world. The average Dutch man is 184 centimeters tall. Assuming the heights of Dutch men are approximately normally distributed with a standard deviation around 8, what percent of Dutch men will be over 2 meters tall? And it even gives you a little reminder here that in notation for a normal distribution, this is what they're saying. It's a normal distribution with a mean of 184 and a standard deviation of 8. Sketch a density curve to illustrate your answer. All right, so in the density curve, it is unimodal and symmetric. We have the mean is 184. 1 standard deviation up, while 184 and 8 is 192. Another standard deviation up would put us at 200. 1 standard deviation down would put us at 176. And another standard deviation down would put us at 168. And we know what percent of the data falls into those ranges. So it says in here, what percent of Dutch men will be over 200 centimeters tall? So what they're asking for is this area right here. This area, what percent of the data fall into that? Well, we can look at our different percentages. I know that 68% of the data falls here. I know that 95% of the data falls in here. If 95% of the data is there, the other 5% of data is in these ends. So that means that there is 2.5% here, and there is 2.5% here. So to answer this question, 2.5% of Dutch men will be greater than 200 centimeters tall. Part B, what is the percentile rank for Dutch men that are 200 centimeters tall? Remember what percentile means? It's the percent of data that fall below a certain value. The percent of data that is below 200 is 97.5%. What is the percentile rank for Dutch men that are 176 centimeters tall? 176 is right here. So take a moment and see if you can figure out what percent would be less than 176. And you should have determined that it is in the 16th percentile. And on the graph, you are demonstrating that there is about 16% of the data that is below 176. Okay, at this time I want you to pause the video and I'd like you to complete the check your understanding on the last page of the activity. Okay, let's check your answers here. For starters, I'm going to write in some notation. This is a normal distribution with a mean of 20 and a standard deviation of 2. So when it's asking how often will you arrive at school in less than 22 minutes, we are one standard deviation above, and that should be about 84% of the time. How often will it take you more than 24 minutes? We are now 2 standard deviations above the mean, but just remember that it's saying more than. So 2.5% of the time it will take you more than 24 minutes to get to school. As always, if you have any questions, please let Mr. Bowman or I know.